So we should be looking at kind of finishing off notes for this unit as we kind of see it, as we have covered a lot of different stuff here. We got a lot of stuff going on with it. These are the notes again for Unit 1 Part C, graphical representation. So we're going to be looking at a lot of graphs and trying to pay attention to what those graphs are telling us. So, are there other ways of finding velocity? We can use position time graphs, and that is a big thing, is to kind of tell us by looking at the slope. And the biggest thing that I saw a lot of students on that activity that we had done previously is not looking at the slope of that line. And being able to understand the slope of that line means that we need to be able to pay attention to what is our y-axis and then what is our x-axis. The majority of the time the time intervals would be on the x-axis. Now, when we look at these pictures on the bottom here, we can see that the first two of them have no curvature to them. Meaning if I took the slope, and when we talk about the slope, we mean the rise over the run at any point through this time, it is going to be the same no matter where it is. Because it's the same all the way around means that the velocity is constant. It might look like it's increasing, but it's not increasing its velocity. The velocity is being held constant because the velocity, as we know from our equations, velocity is equal to distance divided by time. Well, the slope of this line is rise over run. The rise ends up being the displacement. The run ends up being the time. Because the slope does not change, the velocity does not change. And the same can be said for the other graph over here. This rise over run would have a negative velocity. It's constant because the rise over the run is constant. The time is increasing as you go across. The position is changing in a negative direction. So as you go down, when you have that down, it's constant. However, it's just constantly negative. Now, when we have these ones on the right-hand side here, where we have this curvature happening, when they have that curve, that means the slope is changing, because the slope of the line changes as we go on that. Now the slope, and meaning again, the rise would be very small, but the run would be a lot. Here we see the rise is a lot and the run stays fairly constant. Here the rise is a lot more and a lot more, meaning that the slope of the line, the rise over the run, is changing. it is changing its velocity, that means it's either speeding up or slowing down. Now, one way that is kind of a way to kind of, in a way, kind of see, is it constant? Well, if I can draw a line, if I drew a straight line, it would be straight on that line. Now, if I draw a line from the beginning to the end over here and drawing it straight, I can see that there's a lot more of a gap in between my line that I draw and the line that it is, and especially for a position time graph. If there's a gap, that means that there is a change in velocity. It's kind of a rudimentary way of doing that. Now, you could find, if you knew calculus, the curvature of that line would tell you the kind of the slope at any given instant. We're not worried about that. We want to just kind of look at these graphs and be able to interpret whether or not the velocity is constant or if it's changing. The direction in which the line points usually indicates whether it's positive or negative. Now, we can't always say that it gives us the exact speed, but it does tell us a lot of the average, so to speak. At any one given instant, you have to find other parts to it. Because if we find, say, the slope of the position time graph, and again, we have to be able to recognize, and this is where a lot of people get things wrong, is not being able to read graphs properly. It's a position time graph. If it were a velocity time graph, something else would be happening. That slope is giving us an indication of the average velocity, and not the actual speed. The instantaneous is what we want to not say. The instantaneous would have to be zooming in to a very small time interval. Now, because the negative direction, the fact that it's going from a point of 20 to negative, you know, if we said that it was at speed, it would be like, oh, it's 5 meters per second. Well, technically, no. It's actually negative 5 meters per second. Does that mean that the object is slowing down? Not necessarily. It's just moving in that it's just moving in a negative direction. Objects can move in a negative direction and still, in a way, speeding up. It's just speeding up in a negative direction. So we have to be very careful about how we say things. We also, again, need to be extremely careful about what our graph is. Some of the graphs that we will find will be a velocity time graph. Velocity time graphs are telling us something different. But this is, again, a position time graph. So one of the first things you should do when you come upon a graph is identify the X and Y axes labels. When these two cars are side by side, the lines intersect because they are occupying the same position at the same time. Now, one of these cars is already on the screen, and we can see that it's going to be at a position of 20. That just means its graph is going to start at a position of 20 meters, and that's okay. Some people always want to try and get everything to go through the 0, 0 point. That doesn't always happen. We need to scale our graphs in a way that we can see the data easily. not trying to shove as much data on in a small area as possible. So as we see them happening, we can see as the cars go by, we can see the graph for the cars also taking shape. Now, do we know where the red car is? No, we don't. It's just somewhere behind the 0 point, the start point, wherever it may be, wherever the detector is. It doesn't come onto screen or past the 0 point in the Y direction until 4 seconds. That's why its graph doesn't start until the 4-second point. They cross paths at about 7 seconds. What position are they in at 7 seconds is about 60 meters. And so because of that, that is the point in which the red car is passing. We can see by just the rise over run, or the slope of that red car, it is going faster than the blue car, based on what we can see from the graph. We at no time have any understanding whether or not they are ever going the same speed. They are crossing the paths, at 60 meters at a time of 7 seconds. That does not mean they are going the same speed at that point. Their paths are just crossing. The slope of those two at that point is definitely different from each other. So now we see kind of a curvature, and pay attention to the labels that are on the left-hand side of B. We're going to run this a number of times so that we can identify those curves. Now we can see that there are two curves. One of them is very steep curve. One of them is kind of a slow at the beginning and then really speeds up at the end, where one has a constant velocity, and that would be the B. So pay attention to them really carefully. So when we look at these, sometimes it's difficult to see the acceleration if we just look at the cars. If we look at, say, some of the other parts, at their graphs, it's a little bit easier to see the acceleration. And as we can see, at some point, car B and A cross paths, meaning that they are in the same position, but definitely are not going the same speed. At some point, we also see car C eventually speeding up to a point, and it will eventually, probably off the screen, pass car B. So the cars that have that curvature mean that it is accelerating because it is changing its velocity. If the velocity is changing, that means that there is an acceleration. So when we have this, we now have a different graph. Please make sure to note velocity time. Even though this graph does not tell us any numbers, we can still identify which lines are speeding up, meaning they're changing their velocity, and which lines are not. So to verify our... So when we look at these lines, we can see that the A line is as high on the velocity as it is. But the slope of that velocity line is, there is no rise over run. Now remember that acceleration is found as acceleration, change in velocity over time. Now here, if you have no change in velocity, meaning the slope of a velocity time graph, rise over run, velocity over time, if you have 0, it doesn't matter if you're over 100. If you're the 0 divided by 100 is still going to be 0. Therefore, there is no acceleration for line A. No acceleration. And that also means there is no acceleration for line E, because the slope of that line is just constantly at that rate. Now that just means that the velocity is constant. The velocity is constant, meaning there's no change in the acceleration. Now line C has a negative value because it's pointing down. It's a negative acceleration. Lines B and D both would have the same rise over run. Therefore, their acceleration is both positive. So both B and D are your correct answers. The point that D starts with a negative velocity means absolutely nothing. They both have the same rise over run as we progress through. So ultimately, how do we look at different graphs and are able to determine what's going on? If we look at graphs, and we'll write out the full 3 types of graphs, so a distance time graph, a velocity time graph, and an acceleration time graph, we will be able to see the progression of what should actually happen. Now, no numbers are going to be written here, and that's okay because it's all based on concepts and understanding of what's going on. If we see a distance time graph that just has a straight line at a positive distance, or even at a negative distance, the velocity has to be 0 because it's not moving. The slope of that distance or the displacement time or distance time graph is 0. The slope is 0. That means also the acceleration is 0. Now, if our distance time graphs have a positive slope, that means our velocity time graphs are going to have a constant positive, because no matter where I'm at on the distance time graph, the rise over run is the same. Because my velocity time graph shows a constant, when I look at my acceleration time graph, it's going to be constantly 0, meaning it's not accelerating. Now, the same can be said as if I went through and did the negative. A distance time graph for a negative direction, so such as that, would have a velocity time graph that would have a constant negative point. Then the acceleration time graph would also be constantly 0. Even though the velocity time graph is negative, the acceleration can still be 0. Now, what happens when they're curved? A distance time graph that has a curvature to it shows that it's accelerating. How do we know? Because if I take the slope at different points on that line, I will see that the velocity is constantly changing. Therefore, the acceleration time graph would be constantly positive. If the distance time graph shows something like this, the velocity time graph would look something like this. Therefore, regardless of where I'm at, it is always changing. Because it's changing, the acceleration time graph would be a constant negative. So what we look at here and what we can see from this, distance time graphs can have a curve, slope, or straight lines. A velocity time graph can have straight lines or a slope. An acceleration time graph can only have straight lines. A lot of this depends on what each one is doing. If the distance time graph has a curve, the velocity can have a slope. The acceleration will have a straight line. Where on the scale it will be, positive or negative, will depend upon the velocity time graph. If the distance time graph has a slope, the velocity time graph will have a straight line, and therefore the acceleration time graph will also have a straight line. It will just be on the zero. If the distance time graph has a straight line, the velocity time graph will also have a straight line, and the acceleration time graph will have a straight line. And there's the end of our Unit 1 kinematics.